All right. Are you ready, or should I start?
Yes. Okay.
Okay. Okay. So it's my pleasure to welcome Tailin Wu, who'll be talking about machine learning of physics theories. Yeah. Thank you.
Okay. So today my talk is about machine learning of physics theories. So before I delve into the work, I would like to give an overall idea of what I think are the most important things in scientific research. No matter what we are doing is physics, chemistry, or biology, or other disciplines. So firstly, I think one of the most important things in scientific research is to learn theories from either the observations or from the prior theories. And also we want to improve the theories by both simplify the theory and also unify several theories into a master theory. And we also want to propose experiments that can probe the place we are uncertain about. And also we want to understand the system in terms of their constraint and of their objective function, and also the causal relations between the components, and also be able to control the system. We want to, based on some observations, to detect some specific events of the system. And we also want to simulate the system into the future to see how the systems will be in the future. And finally, we want to design some tools to be able to better perform the scientific research. In each of these different things, there are different machine learning tools that can able to help. For example, the work in this talk, I'll talk about AI Physicist, may help us learn theories and improve theories better. And also the symbolic regression can also do the similar things. And also information theory can also help us propose experiments and understand the systems better. And there are other different tools to able to help us do different things. And in each of these combinations, there have been a flood of different works that are trying to use different AI tools to do scientific research or help in different aspects. For example, in particle physics, quantum physics, and also in different condensed matter, biophysics, plasma physics, etc. And each of these different symbols are the different things and different tools they use in their work. So in this work, we are focusing on designing an algorithm that are able to help us learn theories and improve theories better. And specifically, the motivating question is the following. From the AI to physics side, the question is, how can machines propose theories in a similar way as physicists propose theories in order to automate the process? And on the other direction, we also want the physics to help design a better AI tool. And the question is, how can we improve the flexibility and the interpretability of the machine learning using insights from physics? And one of the most important lessons that physics has told us is that if a thing is very hard to solve, then we try to solve the simplest problem that can still capture the essence of the problem. And here, we design a toy paradigm in which there are a ball moving in some domains. For example, here we can see that there are balls that are moving in some domain that may follow different physics laws. And the goal of the system is to figure out what is the dynamics of this ball that it is following. And as we can clearly see that in this left figure, the balls are following different rules at different regions of the space. And similarly, for the right-hand side. And the machines may see something like this, where these are the different trajectories of the balls. And as you can see here, that on the upper left, there are some behavior that is different from here. And the goal is to figure out both the physics laws in each of the domain, as well as the domain boundaries between these without any supervision. So, yeah, for example, the second one is more difficult because the second one is a double pendulum in which we can see that there is two balls here, and then the lower one is in a different electric field, so that when the lower ball is in the upper or lower region, it will follow different physics laws of the whole system. So to very well describe the whole system's dynamics, a very simple and straight idea is to use a neural network to fit the system's dynamics from time t to t+1. But this also has some drawbacks, which is the following. On the one hand, this will not be able to tell us, for example, about the different domain boundaries or different laws it is following. It's just some very uninterpretable weights and biases in these parameters. And also, the other thing, this disadvantage, is that it is not very flexible. Suppose that we come into a new environment in which some of the regions, some of the laws are still the same, but some of the laws are changed. Then we have to fit the whole neural network again without using any of the previous knowledge. So to encounter these drawbacks, here we design a different paradigm in which the focus is on the learning and manipulation of the theories, where the theory here we define it as a two-tuple of a prediction function and a domain classifier. The prediction function tries to predict the system's future from the past, and the domain classifier tries to classify whether the current domain should be applied this theory or not. So the overall pipeline is the following. Suppose that the agent comes into different environment, and in one of the environment, he will try to understand this environment's dynamics. So he will first use the divide and conquer approach we design to discover different theories as well as the domain. And then the learned theories will be put in a theory hub that it can be stored for future use. And then he will also apply the Occam's razor to simplify the theory, and also use the unification tools to unify multiple theories into a master theory. And then when it comes to a new environment, he will first propose some theories from the theory hub if there are some laws that are already learned. And then if there are some new laws that have not been learned, then it will also initiate some new theories to learn. In this way, it can allow the lifelong learning. So, and the overall goal of the agent is to minimize the description length, DL, of the whole description, which contains the description length of the model and the description of the description length of the data given the model. And we designed 4 different algorithms to be able to overall optimize this objective. And I will describe them one by one. So firstly, how do we are able to learn the different physics laws as well as their domain? So we designed this differentiable divide and conquer, which is the following. So suppose that there are multiple different theories T of I, which are consisting of this F of I, which are the prediction functions to predict the future from the past, as well as a domain classifier that predict which of the theory the current data point should use. So to predict some data point x of t and y of t, where the x of t is the past and y of t is the future, different theories may have different performance, because some of the theories can explain very well, but some of the theories may not. So here we can compute a loss function of this theory, f of I. And then we use a generalized mean loss to compute the overall loss of multiple theories on a single data point, x of t and y of t. And for example, if the gamma here is 1, this whole expression is just the mean of the system. If gamma is 0, it will be the geometric mean. And if gamma is -1, it will be the harmonic mean. As we know, if the gamma is less than 0, then the whole average will be dominated by the lowest element of the mean. And then in the end, we sum over all the data points and obtain the overall loss. And then the objective here is to minimize this overall loss. So we prove that when gamma is less than 0, this whole loss will give a larger gradient for the theories that is in a smaller loss. For example, if there are 5 theories that are trying to explain one data point, and one of them is explained very, very well, and the other 4 are not so well, then when minimizing this loss, because it encourages, it is dominated by the lowest loss. Therefore, this best theory will receive the largest gradient from the loss. Therefore, it will allow the better becomes better and worse becomes worse. And it will encourage specialization. And we proved also that this loss can be applied to some generic loss functions like MSE, MAE, Huber loss, and the description loss we will introduce later. And suppose that one theory can explain one domain very well, then it will just fit that domain very well by this loss and ignore the parts of the data that it cannot describe very well. So up to now, is there any question? Okay, so then basically the specific procedure is the following. We first train these different prediction functions using this loss. And at the same time, we feed the domain classifier C to the label of the best model on each data point. So that it's like the prediction function is leading the, is trying to fit, and then this C is following what is the best theory it should use for each data point. And then in stage 2, we freeze the domain classifier C. And now we have a different domain. And now in each domain, we train only the best prediction function to better fine-tune the prediction function. And in this way, we can simultaneously discover both the domain classifier as well as the prediction function of each domain. Secondly, we want to apply the occurrence razor in order to find the overall best theories that can describe the whole system. And we apply it to 2 places. Firstly, instead of using the MSE loss, which has the loss landscape of this figure, we introduce this description length loss, which has the following loss landscape as follows. As we can see, when the error here, which is U of t, is very small, the loss landscape is even steeper. Thus, it will encourage that the loss becomes even near to 0, the nearer it is to 0. Therefore, for example, suppose that we have a few data points like here. The MSE loss will try to adjust to the outliers of the data point. But here, the description length loss will just try to find the points and ignore the outliers. And this is the description length we used to fit the previous domain prediction function. And also, secondly, after we have used the neural network to discover some good prediction functions in each domain, we then apply this occurrence razor with MDL algorithm to even simplify the theory even better. Specifically, suppose that we have learned some neural network prediction functions that can predict the path to the future. But then they are still in terms of their weights and biases. How can we reduce them to some simple symbolic equation? What we do is that we apply some different stages of the simplification, which consist of like collapse layers, local snap, which try to find what is the minimum number of neurons we need to describe from the input. And also we use the integer snap and rational snap, because in physics, many of the parameters are in terms of these simple integers and rational numbers. And finally, we apply the two symbolic equation to transform the simplified equation into a symbolic form. And we find basically what we do is that in each of these simplification, we try some simplification. And after that, we compute the description length of the model as well as description length of the data given the model. And if the new description length is smaller, then we will accept. Otherwise, we will remain the previous model. And in each time, we always try the greedy approach in which we find the best possible way to simplify. So that is the second tool we use. The third tool is the unification. Basically, suppose that we have discovered multiple different theories in terms of their specific numerical values. But then how can we combine them to some master theories? By master theory, I mean there are some parameters. Instead of using the numerical value, we use their parameter to represent some numerical value. And basically what we do is that we first cluster the different theories into different clusters based on their description length. And then in each of the cluster, we find the unifying tree structure of the symbolic expression, and then combine them by replacing the numerical value with the corresponding parameter like A and B, and then it can generalize to more diverse theories. And finally, we apply the lifelong learning, in which we store the learned theories and master theories in the theory hub for future use. So here it is a video of how the learning process is going. And here, in each of the conjoint, there are 4 different laws. And then the color are the learned theories in terms of their different theory domain. And then the size of the dot is the error of the theory on each of the data point. As you can see, that the algorithm are able to discover that there are 4 main different domains. And also it discovered that in the boundary, there are some different theories here and here. And we can fast forward here. So, and then here we see that it learns a much better theory in which the size of the dot is much smaller. So in the end, the algorithm are able that there are 4 conjoint of the theory, as well as there are some boundaries that follow a different physics law. And also for the double-pendulum approach, it also discovers correctly that there are 2 main domains, as indicated by the black boundary. Let me check. Okay. So let me see, there's a question about what if the best theory didn't have a good initial value? Then the gradient will be mostly focusing on the suboptimal theory. Let me think. So basically, what we find is the following. So suppose that we initialize with many different neural networks. Usually we initialize, like, for example, 5 or like 4 or 5 different networks. And there are always some networks that are able to explain some domain better than other neural networks. And then like through the SGD, the stochastic gradient descent, we know that neural network is always able to fit any function very well if the network is expressive enough, because it is a universal function approximator. So yeah, basically what we worry is not like, for example, if some network is not able to fit very well, but instead what we are mainly worried about is the following. Sometimes one network is good and dominate on all the domains, and then it will just fit the whole domain very well, and other networks will just not be able to compete with this theory as a whole. That is the main problem we actually encounter. And when this happens, it means that the neural networks are too expressive, and then we need to then limit the expressiveness of the network, like, for example, reduce its number of layers or the number of neurons, so that each network may not explain everything, but only some places. Yeah. So I'm not sure if I answer your question. Okay. Yeah. So, okay. So here, so there are some quantitative results. So basically here we AI Physicist, we compare with a baseline, which is a single neural network, but with the total number of parameters similar to our current agent. And then we also compare with a newborn ablation, in which we remove the theory hub, so that each time it encounters a new environment, it has to learn everything again. So firstly, we measure the mean square error of the different models. And we find that both the newborn and the AI Physicist in the end are able to learn 10 to the minus 13 in terms of MSE. Much better than the MSE here, because we have the description length loss, and we have the different theories trying to fit different domains. And secondly, the models are able to perfectly discover the different domains without the label, while a baseline, just by random guess, will only get this classification accuracy. And also, we measure how much epochs it takes to reach some certain level of MSE. And we see that the AI Physicist uses much less number of epochs to obtain some certain MSE value. This means that with the theory hub, they are able to propose some learned theory. It is able to learn quicker. And also, in the end, we also see that only with like 1% of the data, the AI Physicist is able to reach like the 10 to the minus 2 MSE with very small epochs, which means that this will also allow it to learn more efficiently in terms of the data requirement. So here is an example of a specific process. Suppose that after the first domain differentiable divide and conquer, we have learned a network, and then we have collapsed the networks into this one-layer network like this. And then the description length of the model is 212, where here we measure the description length in terms of what is the number of bits it takes to represent each of the number. And a floating point has much more bits than integer or rational number. And also the error here is like this. And then after some after the second algorithm, in which we use the different greedy things like two rational number and two integers and so on, the algorithm is able to find some integers to snap into, so that the description length of the model is much smaller. And also we see that with this reduction, actually the error becomes even better, slightly better. And then we transform that into a symbolic equation like this. And we can find many different symbolic equations where it's with different numbers here. And then using the unification, we are able to unify them into a law like this, where these are P1 and P2. Yeah, this is a simple demonstration of how this works. And so now I can discuss about the generality and limitation of this work. So firstly, although our work is designed and tested on a toy paradigm where a ball is moving in some domain, this framework can actually, in principle, tackle many different general domains. For example, it is able to tackle arbitrary number of input spatial dimensions because we can use a neural network to fit those different input. And then we can also adapt to different spatial domains, not necessarily the square domain, but any boundary condition. And also, it is able to deal with different past time steps used, and the boundary, and also evolutionary laws of arbitrary complexity. Let me see, there's a question. Oh, so symbolic. So basically, symbolic means that basically there are two main forms that we can use to describe some equation or some dynamics. One is the dynamic neural network, in which we can express how the past to the future is represented as a neural network of multi-layer network. And the second way is to represent them in terms of symbolic equations, like this, in which we use some symbolic equation instead of a neural network to represent it. And both forms are equivalent in the sense that we can always transform one form to another. Just that, like some forms are actually it's like this. We can always transform a neural network into some symbolic equation, but the symbolic equation may not be easily transformed into a neural network. For example, suppose that we have some square root or some exponential number or sign, something like this, then it will be very hard to transform into a neural network. But on the other hand, a neural network can still try to fit any symbolic equation. Yeah, so there is some generic correspondence between these two. And in physics, we generally want to, in the end, obtain some symbolic equation that are more simple and better interpretable. So do I answer your question? Okay.
I'm not sure.
Okay, so what's your question specifically?
Like, what can you talk about symbolic regression?
Mm-hmm.
What's the meaning of it?
So the question is, can I talk about symbolic regression? Is that your question?
Yeah, if you can explain it.
Yeah. So the symbolic regression, I can use this, maybe this slide here to represent it. So basically, a symbolic regression is the following. Basically, given some input and output pairs, like, for example, suppose that we are given like the past as input and the future as the target. We are given this data, and then we try to use some tools to discover the symbolic equation that map the input to the output. For example, this is some discovered result of the symbolic equation, through the symbolic regression from the AI Feynman work.
So in neural networks,
Mm-hmm.
you have training and prediction. So past and future can be exchangeable with this training and prediction.
Okay.
So how symbolic approach or formulation helps me to deal with this?
Oh, so let me see. So basically, it's like this. This depends on the goal, our goal. So if we just want to find a model or learn a model that can map the past to the future in a very precise way, then we can simply fit a neural network to the data of the past and future, and then by some tuning and learning, it will always learn the past to the future very well, because we know that the neural networks are generic, universal function approximators. But the thing is that once we have this network, it may usually be some multi-layer neural network where there are maybe thousands or even millions of weights and biases, which are maybe very hard to interpret. And we may not gain much understanding about what would be a more simple description of the system. For example, we might want to, in the end, discover for example, the E equals NC squared, or something like the Maxwell's equation, which are very simple. And then if our goal is only to just fit this input, this past to future very well, then we are done. But if we want to gain more understanding, then we might need some symbolic regression in which it can still describe this very well, but in a more simple form.
Okay, thank you.
Yeah. Yeah. So here is a question about comment about the symbolic regression versus the sparse regression with dictionaries, like Cindy. So let me see in terms of noise and something else. So I think that these two different fields have some much overlap. Symbolic regression, we can think of it as a more generic term that tries to use any some specific or any different ways to derive a symbolic equation from the input-output pairs. And the sparse regression, I think it can be generally think of as, like, for example, one specific way to find find this find this expression. Like, for example, sparse regression uses the like L1 or other ways to limit the number of like dictionaries, the number of terms it will try to explain the system. So I think that these are two terms that are different domains that have much overlap. And so in terms of the noise, yeah, I think the Cindy type things are very robust to noise. And depending on the different ways that we do symbolic regression, it may be more or less prone to noise, which I will explain later. So yeah, I will explain later about the noise issue. So going back to here, so there are also some limitations of this work, which is, for example, in this work, the simplification procedure is limited in the sense that we only tried a few different procedures, like, for example, to integers or to irrational numbers, and so on. And also, the other limitation is that we need to provide the agent with the actual state variables, like for example, what is the current position and also the current velocity of the system. And suppose that we give it the image or the video, then it will not be able to discover those relevant variables from the raw pixels. And thirdly, it is not able to reason with some physics concept, like for example, mass or like force in a similar way as humans. And we also have some analysis capability, like for example, we use the different ways to simplify the theory and also use different ways to unify and so on, but it is still limited and hand designed. So to address these limitations, later Max Group developed some more ways to address this limitation. For example, in the AI Feynman work, it is entirely devoted to the symbolic regression, in which we basically design a pipeline to perform symbolic regression on some very complicated dynamics. For example, the AI Feynman follows this OverRaw pipeline, in which the overall idea is to use the divide and conquer, in which, for example, given some data of the input and target, it first performs some dimensional analysis to, for example, resolve the dimension and reduce the number of variables. For example, let me show you a simple example here. So suppose that we want to have some equations like here, which are this equation, and then you can perform some dimensional analysis to distill something out, and then the equation becomes non-dimensional, and then it becomes like this. And then it first, for example, tries to see if there are some symmetries of the system or some other different ways that you can simplify. And then you can simplify it in terms of this. And then now you will also find that this equation can be separated into two equations, which has the multiplicative separability. And then like here and here. And then it will basically doing some polynomial fit and also invert to better discover each component. So basically what this overall does is that it recursively tries to decompose the data into different parts depending on whether it discovers some symmetries or some ways to decompose. And then in each of these parts, it will recursively use the, like for example, some basic way like polynomial fit or some brute force to discover the actual equation within it. And if still cannot discover, it then try to decompose again and then recursively go down until you are able to only fit with like a polynomial. Yeah, this is the gist of this work. And so, but in this work, it is very prone to noise. And for example, it may not be able to resist the noise up to 10 to the minus 4 or 5. And then in the AI Feynman tool, we improve this method in which we use a neural network with gradient to further, before fitting the data, we use the neural network to fit the network, the data, and then use the gradient to see if there are some more symmetries or component that we can decompose. And then use these discovered graph structures and apply it with the AI Feynman, this pipeline. And also, we use one more trick or technique, which is the Pareto frontier, in which basically, suppose that there are multiple different equations that can fit the system reasonably well, and they can lie on a Pareto frontier on the axis of the error and also the complexity in terms of how complex their equations are. And for example, for the equation of this like energy depending on the mass, we have in terms of different complexity, you can discover that there are this Newton's law, and then in the end there is the Einstein's relativity, and they all lie on a Pareto frontier. That if you have more complex equation, then you can fit the data better. And there are also many other points in the inside of this Pareto frontier that the agent will discard. And basically, instead of previous AI assignment in which we only use one point that minimize the total description length, here we always keep a Pareto frontier of all the data, all the different equations. And this helps us to improve the robustness of the noise from 10 to the minus 4 to 10 to the minus 2. Like here, for example, in the end, many of the equations are able to like release the noise up to 10 to the minus 1. And these are the some of the equations we discovered using this pipeline. Any questions up to now? Okay. So, and also to address the problem of like we need to come up with the actual state instead of the raw observations. And then Max also have one work that are able to use some autoencoder to learn some latent variable from which it can then try to discover the equation on the latent variable. And then for the last two aspects, yeah, there are some projects we are working on in which we try to deal with these limitations. So this work, although it is in the physics domain, the implication is also, we also have implications in AI. And basically, it connects to the causal learning and learning world models and future learning in the AI community. And suppose that we can have a better model that can continuously learn and able to summarize different parts of the domain very well, then it can better learn it with fewer shot and able to learn some causal relations between different variables. And then in summary, our goal is to apply AI to address many of the important physics or other scientific problems. And in the end, we hope that we can use different AI tools to address different things in the scientific research and help advance science as a whole. Thank you. Any questions?
Yeah, thank you. Yeah, any questions? I had actually two questions. So
Yeah.
one is about scale invariance. I mean, when you talk about unification, is there, are you restricted to one particular scale, or can you go from through different scales?
What do you mean by scale?
Yeah, for example, like extreme case would be unifying between quantum mechanics and general relativity.
Oh, I see. So yeah, so here in this work, we are mainly like develop a very simple unification, which is like for example, suppose that different symbolic equations have a similar tree structure, then we unify them. But actually, there are many different. This is only a very small proportion of what can be done in here, and there can be much more things that can be explored in this area. We definitely are not able to do it now, like combine, like for example, generality with quantum mechanics. That would be the dream of every physicist. But I think like this is a very worthwhile area to explore. Like, and I also think that like unification, it is not only in terms of the symbolic form. Like for example, suppose that we already have some state variable and then we have some model that can have a symbolic equation and then we unify them. It is more about in the conceptual level. Like for example, like when Shannon proposed his information theory, he distilled information, the concept of information, from many different domains, and captures many of the different domains essence of communication. And I think a more interesting area is that how can we distill some concept that is the unification of multiple different domains, and then discover what this concept is obeying what laws or what is its dynamics. And I think this will be also a very interesting area to explore. But we also need to study that. We need to like design some simple domain that still captures the essence of this problem so that it is manageable, and then work from there.
All right, thank you. So then Amel, do you have a question?
Yes, I was wondering, can you learn, considering Mercury's orbit, can you learn the geodesic equation? That would be, have you tried that?
So do you mean just learning the Mercury's orbit, or do you mean learning this procession?
I'm wondering, because this is already a jump in understanding where you need to replace the Newtonian laws of motion or Newtonian gravity with general relativity, or you have the geodesic equation that describes the motion of planets. So I was wondering, it's difficult to see how it's going to come about automatically, and I was just wondering, do you have any hope of actually learning that?
I see.
Because you have Christoffel symbols and so on in there, and it's a curved space-time, and I was just wondering, can this, since in a way it's similar to what you have in the kinematic case, where you have mv squared, right, and then you have this generalization of it where you have the energy in special relativity. But I was just wondering now, could you perhaps do the same but for general relativity?
I see. So I think there are, so let me describe it in this way. So right now, the whole system, no matter the AI physicist or AI Feynman, the problem formulation is the following. We always are given, for example, some the state of the system from the past and future, like x of t, and then x of like t plus 1. And then we try to find some very good description and simple description from the past to the future. And like if we are given this data in a very, very precise way, like for example, we are given the position and velocity of like Mercury in very precise way, then I think it is in principle able to discover, for example, this like very precise laws beyond the Newton's gravity. Like for example, it may have this general relativity component, but it will be shown in that equation, in the specific equation, the symbolic equation we discover. But then this is not the whole thing of the story, because how to interpret this equation is also very important, right? For example, suppose that we discover that there are some deviation from the like gravity law, and how to interpret this. And our system right now is not able to interpret this. It is only able to, like for example, discover what equation in the end it may follow. And for the problem of how to interpret, then I think it needs far more things. Like for example, it will need the concept of like space, time, and also like for example, the geometry of the space and so on. And then you need to, for example, build some connection from those different concepts to the equation you discovered. Yeah. So yeah, right now we are able to help to, for example, to discover the symbolic equation point, but it will be a very interesting work to explore how can we help, for example, in combining those different knowledge to interpret the equation. Do I answer your question?
Yes, thank you.
Mm-hmm.
Any other questions?
Yes.
Sorry, go ahead.
Can we relate or think back to the world before this beautiful, fascinating framework, which is very promising, but can we think about difficulties that we had in convergence, like a tipping point, turning point, saddle points, global minima versus local minima? Do you encounter difficulties like this in, let's call this higher level framework?
Do you mean those, for example, global minimum and local minimum during the learning process? Or do you mean...
I believe that if I give a neural network a situation of cusp or saddle point where the derivatives are not well defined, the neural network will spit some garbage. That's what I believe, although I never ran a neural network. I used Newton method for convergence to find minima and so on. But, and I know that if the initial guess for the Newton method is too far, it also fails. So the question is, what is the probability of failing to find the right law or the right goals of this framework, which are very conceptually very developed and high level?
I see. Yeah, that's a very good question. So as I previously described before, one difficulty we encounter is that the neural network, one neural network may dominate the other network. So actually, in the domain of using the neural network to feed some data, like because the number of parameters the neural network has usually is very large, it usually has different dynamics than, for example, if you're just fitting a model with a few parameters. Because like, for example, suppose that we fit a neural network with like 1,000 or even like 10,000 or 100,000 different parameters. There are some study that says that usually these networks have many different local minimums, but then those minimums almost have the same loss as the global minima. And usually you can think of their landscape as usually very flat around the region of local minimums and so on. And usually you are able to find, if you train very well, you are able to find some reasonably good parameter. But actually, yeah, there are also some work that shows, for example, that one of the problems in neural network training is the saddle point, because it is not a local minimum. Because in high dimensions, it is much likely that one point, one stationary point, is a saddle point instead of a local minimum. And then around those saddle points, it will be very hard to learn because the gradient there is very small, and then it may take exponential time to escape that saddle point. But then there is also ways to counter that, which is using some noise during learning, like, for example, either the stochastic gradient descent or adding some gradient noise and so on will help it escape those saddle points faster from exponential time to polynomial time. Yeah, so this above is like how do we better train the network, and any development there will help us in this framework, because this framework here is proposing a high-level paradigm, but how specifically like networks are learned will be always dependent on the specific development of the field. And we do in this current system, we do not find the problem of saddle point very, very severe. Usually we are able to find some very good minimum. Yeah, sometimes we have this issue of the one network having like this like be the best for all the regions. If that happens, we just retrain it. And like in this work, like we take the minimum of the 10 different runs, and usually, almost always, it is able to discover a very good loss, like here.
That's beautiful.
Yeah.
But I may have a comment about the noise, because a few minutes ago you were talking about being robust to noise. And
Yes.
then when we get stuck, we need to invoke the noise. So how do you reconcile that when I'm walking in the dark and I don't know where I am?
I see. So the noise here actually are different on different target. So when the question mainly was asking about the noise in the input and output variable we are given, and suppose that we are not given the actual state, but actually we are given some observation that have added some Gaussian noise to the input and output, and how the system is able to discover the law regardless of that noise. So, and that robustness to noise will be very important for any of these algorithms. And we have discovered, for example, using the Pareto frontier, it can help reducing this sensitivity to the noise. So for the noise in the learning, that is a different story. The noise in the learning was added during the optimization of the parameter, not added to the input and target. And usually in the learning, people have found that having those noise will help you discover a better minimum, a more like, for example, wider minimum that generalize better and also be able to escape the saddle point better. And when adding that noise, it is not added to the input and target, but instead added to the parameter of the model. And it is also some an art to design how much noise do we add, and so on. And basically, the noise added to the input observation, it is out of our control, and we cannot, like, for example, hope that it can give us better data, but we are just working with the data. But for the noise in the learning, we can always try to improve its usage. Like for example, we can observe the loss during learning and see if it converges to a better minimum in terms of their loss, and so on. And we can just tune this noise scale and how do we schedule the noise to be able to better learn the model.
Thanks, that's lovely explanation.
Mm-hmm.
Thank you.
Yeah, thank you.
Thanks. Any other questions?
I was wondering if these libraries are available. Have you made them publicly available? Because
yes.
it looks like a lot of components. So.
Yeah, so if you just search AI Physicist and GitHub, you will find the GitHub library. Do you mean the code?
So both AI Physicist and AI Feynman as well.
Yeah. Yeah. If you search AI Feynman and then GitHub, you will also find the library of the symbolic regression. And also one good thing about the AI Feynman is that you can just pip install. Like for example, pip install AI Feynman, and then you can just prepare the data in terms of CSV, like the input and output, and then you will just run it, and then you will get some result after half an hour.
Oh, very nice. Thank you. Mm-hmm. Another thing I was wondering about was what happens when you have some underlying variables or latent variables that you don't have access to. So, like for instance, suppose you have two mergers of black holes and you have just this 1D data set. I was wondering, how do you deal with projection effects and so on? I suppose there's a lot. How do you deal with cases when there is much degeneracy?
So you are saying that suppose there are two black holes, right? And then they are merged. And what is the data you are given?
So the data is like a 1D strain. So the data is like 1D, but the problem itself is a many D problem, right? Because it depends on like the spins of the black holes and the masses and so on. So I was just wondering, how do you deal with how do you deal when you only see like a part of the space, or you only see like a projection of the dynamics?
I see. So basically, you are saying that, for example, suppose that I have a black hole, and each black hole will have their state as like position and also the velocity, right? But we
so they will have their positions and velocities, yes, and they will have their spins as well.
Yes.
But what we observe on Earth is just a 1D signal of like the gravitational wave itself. And,
I see. Yeah, I see. And what's the goal?
So in the end, I would like to know what is actually going on, right? So I got this like 1D, you could say, this wave pattern that I have in my detector, but actually I would like to learn the physics behind it.
Yes.
And so is there any hope of since this is a projection, or this is only, you get partial information because you get only this one piece, or you get this gravitational wave and it doesn't have all the information. I was just wondering how this is you could say this is you getting partial information about the physical process. You're not seeing everything moving. So I'm wondering how can you learn? How can you hope even to learn this underlying system?
Yeah, I think this is a very good question, because this happens all the time in all different places, right? For example, you always observe something, but it is a projection of something else, underlying things. I think, this problem is also the domain of the current work. We can, we can brainstorm about it right now. Basically, it's like this. The goal here is that from this observation, you want to, for example, understand what is the underlying dynamics of the system that generate this observation. So basically, then we have some unobserved state variable. Like for example, we can have some x of t, where x here is a vector of all the unobserved variables that will go from x of t to xt plus 1 and so on. And then we also may have a function that map the state to an observation. So suppose that the function is g. So we can have O of t equals, do you see the, here, I can make it larger.
I see it, yes. It's,
yeah, so yeah, we can always, for example, map some latent state to some observation here. And this observation may be the 1D thing you are talking about. And then this xt is the underlying, for example, the two black holes and their state and so on. So your question formality is the following. I'm only observing O of t, where t is like 1, 2, and so on. How do we, for example, learn three things at the same time? One is the g that maps the state to the observation, which is this g function. Actually, the first thing we need to learn is what are the relevant variables we want to have, which is what is the x we want to have. The other is what is the g that maps from this to O. And the third thing is what is the dynamics law that maps, for example, f from xt to t plus 1. So I would say that if you are not given all three of them, and you are only given the O of t, then there can be many different explanations about, for example, what the x will be and what the g will be and what the f will be. Because, for example, suppose that I have a ground truth of this, then I can always redefine a new variable, like, for example, a y variable, maybe like u variable, which is a function like h of x. And then as long as this h is invertible, then I can always describe the whole system in terms of u and their observation function. Like, for example, the g prime will be something like g with, for example, h minus 1, something like this, and then and so on. And f will be h minus 1 f h, something like that. So there is a degeneracy here. But there is one thing that may be constant, which is no matter what these degeneracies are, there must be a space that no matter how you transform this, there is some variable. Like, basically, it's like, I think if you live in a space up to some invertible function that you can apply it. And then because you always need some latent information that you can describe the system's evolution, there must be some amount of information that you cannot compress. Yeah, so then what we may find if we are without these three information will be some manifold in which any of these one is a good explanation. But if we know some more knowledge, for example, if we have a vague idea about the g function, like how the potential state may generate the observation, then it will pose some limitation on the g here, from which we can limit the state better. Or if we know some symmetry about the x of t, like, for example, we require that the x of t should be translational invariant, then we can also impose it on the f, design of f. so that we can limit the space F even better. Yeah. In the case of your black hole, you may well assume that, for example, like we know that there are some bodies, and the bodies may have interaction, and then their interaction may induce some observation. The more you know about that, the more you are able to limit this F better, and then able to discover potentially the law. For example, suppose that you are able to find a good G and a good state variable and good F that can predict the O very well. Then you can then apply the symbolic regression on the F to discover what is the equation there.
Thank you.
Yeah.
Other questions? I had a question actually. So when you come back to the table of the laws that you were showing.
Yes.
Yeah. So not this one, but I think there was another table that.
Let me see. Yeah, that one. Here.
Yeah, exactly. Yeah, exactly.
Yep.
So here I was wondering. I mean, are there cases in practice that where you show that your laws are better than the existing laws?
So actually, this table is like, for example, it compares the AI Feynman with the AI Feynman tool, and then it shows that, for example, previously how many expressions can only up to 10 to the minus 3, and then now are able to do 10 to the minus 2, for example.
No, what I meant is not about is not robustness to noise. Is yes. Cases where these new laws in a way are more valid than the other ones, or are valid while the old laws are not valid. I think it's very similar to what Ahmed asked you initially about Mercury periphery, where you have where you have general relativity applies, but classical physics doesn't apply. But I was wondering if you already discovered something like that in practice, where laws discovered according to your this AI Physicist or AI Feynman are valid while existing laws are not valid.
I see. So so in the AI Feynman work, like what they used is like the 100 equations in the Feynman's lecture, and then they are able to like almost recover all of the equations from the data, and we have not tested on like discovering new laws. Like all of the current ones are like existing ones.
Okay.
And also in terms of like, for example, which laws are better. Like for example, we take this for example. Like for example, we may discover that this law is the best up to some certain complexity, and so on. So I think any laws on the proto frontier can be of some usage, because it depends on how much complexity we accept, and so on. And therefore, we may say that this is better in terms of the accuracy, but it may use more complexity here.
Yeah, all right, thank you. Any other questions? All right, then. Thank you very much for the nice talk. It's very good. Yeah, thank you.
Thank you.
Yeah, thanks a lot.
Yeah, thank you very much.
Bye-bye. Thanks. Thanks, everyone. Bye-bye.
Bye.
Bye.